Welcome to Lecture 14. We continue our journey into models for agents and the environment. We've started at the case when we have static environment where the agent receives stimulus from the environment in the form of rewards and punishment. And then we move on to models like MDP or Markov games where the agents are utilizing the dynamics of the environment. So the agent have an impact on the environment by performing actions. So one of the underlying assumptions behind all of the work that we've looked at so far was that even though the agent was not fully aware of the state of the environment, or not fully aware of where the environment will go given a particular action, the agents all have some sort of prior belief in the form of probability distributions about potential transitions of the environment. So they have some sort of rough idea about what will happen if they perform given actions. It's just that these ideas are probabilistic. Right, but what this underlying assumption means is that in the agent's mind, there is a model of the world, and even though this model of the world may be randomized, it still captures very much the dynamics of the potential interactions between the agent and the environment. This assumption may be problematic in real life when we are designing artificial agents that are functioning in a more complex situation or in a completely unknown situation, right? So there are cases where potentially this model could be extremely large. It contains huge number of states with transitions among them. It's just unpractical to explicitly come up with the probability of the transitions beforehand. And also notice that the other sort of randomized factor is the reward. So before we assume that the agent are fully aware of the system and sort of the reward that are associated with each transition. But this also can be difficult to review in practice. For example, when we want to develop an agent that's deployed in an unknown situation, in an unknown environment, then it's impossible to identify the transitions or the rewards that are associated with those transitions. So in this case, we are in this real world situation that we do not really have a prior model that are associated with the environment. Nevertheless, the agent will still need to be able to act, and hopefully in an optimal or in a very good way. So this brings back the paradigm of learning, right? So we would ideally, in this situation, to implement learning capability to the agents in order for it to essentially find a good way of performing their tasks in an unknown environment. Right? Notice that the last time we talked about the issue of learning was when we look at repeated games and the number of agents who are in the environment, they are learning about each other. Right. That was okay when the environment was completely static. So we did not assume that the environment could change. But now with this more complex situation where the agents are interacting with the environment, there is really a need for the agent to be able to understand what's going on in the environment, and so what sort of transitions could take place, assuming that the environment is a Markov decision process. We will ideally be able to find the probability of the transition. We will ideally be able to find the probability of the rewards. So this brings the need for what we call reinforcement learning, a paradigm of machine learning that allows agents to evaluate the environment and to approximate the environment in order to build a rough model of the environment, and with that find the optimal control. Right. So another name for reinforcement learning is learning by trial and error. So essentially, the agent will be able to, even though there's no model to the environment, the agent will still be able to perform tasks within the environment. It's just that we cannot guarantee that the performance will be good. But based on the result of the performance, the agent will be able to learn about the optimal way to function within the environment. Right. So this is reinforcement learning. I encourage you to find some videos online or some material in other books or papers that discuss the sort of the philosophical roots or psychological roots of reinforcement learning, which I'm not going to do right now. I'm just presenting the algorithm. So now we're going into looking at learning, but again, we're just starting from the very basic situation. So here we are handling the situation where we have an MDP, but instead of a truly dynamic MDP, we just have a sort of a static environment, right? This is a single state MDP. This means that the environment does not really change. So the agents are able to perform a number of actions and receive rewards. The reward function is probabilistic, so it doesn't. So when we perform the same action, we do not necessarily get the same reward. So the reward function follows some sort of distribution, but nevertheless, we would want to be able to find the best action so that we can get the biggest rewards out of doing these, out of making these decisions. And also, just to make our life easier for now, we are again going back to the case when we have a single agent. Right. So in this lecture, I'm only looking at single agent reinforcement learning. In the next lecture, we'll briefly talk about multi-agent. But right now, let's just try to imagine that there is a single agent who is in a unknown environment, and the agent wants to develop an understanding of the environment. So now imagine this case. Suppose just in front of your house, there's a new ice cream parlor that was opened. And you've never been there. Once you go in, you see a whole range of different exotic ice cream flavors, and of course you're very picky on the flavors. So some of the flavors you like really much, some of the flavor you just hate, some of the flavor just so and so on. So you would like to taste ice creams, but you also want to get the highest satisfaction from the eating of the ice creams. So what should you do? Right. So essentially, this is a situation where you see this. Essentially, we're facing a static environment. Right. The environment is offering all of these flavors of ice creams to you. It never changes, and the reward function is unknown. Right, because you don't know how much satisfaction each flavor of ice cream will give you, and you want to learn about it. So you wish to uncover the reward function from each of your actions. And how do you do that? Right, you cannot get to know that without tasting the ice cream yourself. So this corresponds to taking sample runs of the MDP by performing actions and then observe the reward, because reward is a stimulus that the environment provides to us. Obviously, as an agent, we would be able to look at the reward that we get, but because of the samples are sort of having noisy reward, if we just taste one ice cream once, we get a satisfaction, but that's not completely reliable. So maybe the second time it gets better. Right, so that's the situation. And more formally, we have a set of actions. And then with each action, we have a random reward variable, which is called RA, where A is the action. And then the distribution of this random reward variable is unknown. right? It could look like any of these shapes below. So in fact, this diagram give you an example where we have 5 random variables, each one with different distribution. However, as the agent in the environment, you have no idea about these distributions. And what you want to do is you want to try some of the ice creams, and based on the reward that you get, you want to be able to somehow maximize the overall rewards that you get, right? So you want to decide on the sequence of actions A1, A2 up to AT, such that the sum of the reward that you get out of that sequence, remember these are noisy rewards, right? So each time it is just taking a sample from the corresponding distributions, but what you want to do is you want to maximize the expected total reward. Right, so this is what we call K-armed bandit problem. It a notion, the word comes from gambling, right? So you have these gambling machines where it has a number of arms, and then you want to choose an arm which give you the highest reward. So essentially, you can think of the action of taking samples of ice cream like it's like a gambling, right? So imagine you're just a person who really likes ice cream, and you go into this shop. There are 2 types of people, so you may be one of them. One of the type of person is really curiosity driven. So when they see these many exotic flavor of ice cream, this person would like to go over all of these types of ice creams, as broadly as possible in order to get an idea for everything, right? So this is the sort of what we call the exploration type of person, or explorative type of people. The other type of people is on the other extreme is a person who really does not want to waste a lot of time, but instead they just go for some of the ice cream that they look to be good, well, maybe just a very small fraction of all of the ice cream flavors, and then find the one that they like best, and then just stick to it. Right, so they just never change their mind. And so from now on, they would just ignore any of the other types of ice creams. So this sort of people are what we call the exploiters or exploitative persons. So they perform exploitation. Right? There's two type of people: exploration based and there's exploitation based. And there's a classic dilemma between this. Right. So if you are exploration, this means that you want to get as much knowledge as possible to the environment. But then the outcome of that may be that there could be a lot of flavors of ice cream that you just hate. And if you try all of them, then you are wasting all of your samples on these bad ice cream. So at the end, the total satisfaction will be quite small, even though you've got a lot of knowledge about everything, right? On the other hand, if you are exploitation-based type of person, you can sort of guarantee that you do not get the worst type of ice cream, but because you're ignoring so many other tastes, it means that you are very unlikely to get the best taste for you, the best type of ice cream for you. Right. So the trade-off between exploration and exploitation basically says that, well, suppose we want to find the best type of ice cream, then you really want to try those ice cream that you do not like. Right. So in another word, to make optimal choice requires performing suboptimal actions. Right. So when we are facing this sort of scenario, and this is a classic scenario in any sort of reinforcement learning scenario where we do not know about the world, we do not know about the reward function, in order to find the optimal strategy, you will need to balance exploration with exploitation. Right, and that forms one of the most crucial aspects of reinforcement learning. So how do you actually make this nice balance and learn about the outcome of each of the possible actions that you can make, I'm going to introduce these very classical scheme. And it itself is an algorithm, and it's also a technique that can be integrated into a lot of the other algorithms that we will introduce later. So this algorithm is called the epsilon greedy method. And essentially, it's a way for us to balance exploration with exploitation. So just stay with the situation where we're looking at K-armed the bandit problem, right? So we have a number of actions, and we take any action A, and then pick a natural number T. We use capital QTA, so again, this is the Q value that's defined on this action, to denote the estimated rewards given that A is selected in the T's trial. Right? And we make a fundamental assumption that, so first of all, the samples that we take must be consistent with the true distribution. Right, so this means that when we take a sample, the reward that we'll get was actually sampled from the distribution of that action. Right, so that these are consistent. And also, all of the samples are taken independently from each other. Right? And in this case, what we could do in order to learn about the reward, and also one of the other assumptions is that we care about, well, because it's a big distribution, we're actually caring about the expectation of the reward. So we were actually looking for the mean value of the reward distribution. And because the samples are taken in consistence with the reward distribution, also they are also taken independently from each other. If we look at the empirical mean of the rewards out of taking that action, that should be getting closer and closer to the true mean of the reward distribution for that action. Right? So this means that if we have a number of samples, and the more samples that we get, and if we just look at the empirical mean, that's just the average value of the reward that we get out of all of the samples for that action, that mean should get closer and closer. So that will be a reliable approximation to the true mean of the reward distribution. Right? So this is exactly what we're going to do. We're going to just compute or approximate the value QTA by taking the sum of rewards when A is taken before the T's trial. So we look at all of the reward for all of the time when A is taken, divided by the number of times that A has been taken. Right? So mathematically, this is the sum of all of the I less than T, where you have AI is equal to A. So at that I's moment, we chose action A. We look at that reward that we get. We take the sum of it, and then we divide it by the number of times in which AI is equal to A. Right? So that average number, that's QT of A. Right? So essentially, the algorithm just asks us to approximate this value, but then the question is, how do you pick your action? Right? If you look at all of the actions, you'll be able to compute for each one a Q value, and this Q value, according to the analysis, is an approximation to how good this action will perform. Right? So if you are an exploiter, so if you really like to make exploitation, then an obvious choice for you is to always pick the A, which gives you the maximum QTA. Right? But the dilemma comes as when T is very small. This means that when we have not made a lot of samples, these QTA may be quite far away from the actual mean value of the reward distribution. So even though some action may give us a high QTA, it may not actually be reflecting the true performance of this action, right? And there's a need for us to still not try only the action that has the highest QTA value, but also there's a need to try some of the other actions, just to build up enough experience for us to reliably say, which action will give us the highest reward, right? So the action of the selection of a greedy selection correspond to we always pick the best action given the current evaluation. So this is exactly exploitation. Because given QT, we just take the action which gives us the maximum as the current AT. So let's rearrange the calculation for taking the average of all the rewards. So here we do this to build up a incremental or an online update to the average function. In fact, we don't need this, but for every iteration, we don't need to actually compute the average. We can iteratively keep track of the new Q value from the existing Q value by this sort of formulation. So if we want to compute Qn plus 1, remember this is the function at the just before the n plus 1's trial. Right, so we assume that we have taken n samples. Then we look at all of the. So suppose we have made these samples and all of these samples are on a particular action. Right, so we look at the reward that we get. We add up the reward and we divide it by n. Right, that's the average reward that we get. We can rewrite this by expanding this out into Rn and plus the sum of all of the Ri's where I ranges from 1 to n minus 1. And then with some algebraic manipulation, we'll be able to derive that this in fact will be equal to 1 over n times inside the bracket we'll have the last reward that we get plus n minus 1 times the previous Q value, right? So this is how we update the new Q value. To obtain the new Q value, we take the old Q value and then we apply this operation. And if we rewrite it, then we can write Qn plus 1 as the Qn, so which is the previous evaluation, previous expectation, plus 1 over n, so it's actually a very small number, multiply with Rn minus Qn. But now if we imagine what is Rn minus Qn, remember Qn was this average value out of the n minus 1 samples that we've taken. And Rn is the reward, the actual reward that we get in the nth time that we take this action. Right? So if in fact this Rn minus Qn expresses some sort of error, right? The Qn is our expectation and Rn is the target value that we aim to capture. And by taking Rn minus Qn, this would really give us how much error there is. If it's a positive value, it means that this Qn is somehow underestimates the reward. But if it's a negative value, it means that Qn overestimates the rewards. Right? And then in order to adjust our estimate, we take the existing estimate plus a very small fraction of the error. Right? It could be either positive error or negative error, but it's adjusting the estimate that we have. If we overestimated the reward, then this value will be negative. So the new Q value will get smaller than the previous one. But if we under-evaluate the reward, then this error will be positive. So the new evaluation, Qn plus 1, will be bigger than the previous evaluation. Right? And all of these are actually trivial if you look at it as just the average of all of the rewards. Right? But this underlines a very important rule, and this rule is universal in reinforcement learning, which is so in reinforcement learning we constantly evaluate the actions that we could make, and in order to also reinforcement learning is a scheme that's based on updates of experiences. So we may have made a number of experiences in the past, and we have made an estimate out of those experiences. But these experiences are always not reliable to a certain degree. So once we make a new sample, so once we gain some new experience, we will need to evaluate the difference between the outcome of that new experience and our estimate. And then based on the difference, we will make an update to our estimation. Right? So this can be formalized by writing new estimate as being updated in this rule. So we take the old estimate, we plus some small number, in this case it's just a step size, somebody call it a learning rate, but it's some small value, and is multiplying the target minus old estimate. So this is minus, this is the error that we get. So old estimate plus step size multiply error. That's our new estimate, right? So how do we perform epsilon greedy selection? We do that, but we also add in the possibility of exploration. So we're not just doing exploitation, right? So what we do, so the input consists of these number. So in fact, this k would be the number of actions that are available to us, and we assume that these actions are 1, 2, 3, 4 up to k, and t is the number of samples that we are willing to make, right? Of course, the more samples, the more accurate our learning will be, but there has to be some sort of fixed number. So we say that we're going to repeat this learning for t rounds. We're going to take t samples, and then we have a reward function, but this reward function is unknown. So it's a unknown function. So we can only obtain the output of that function. So this reward is currently a black box, right? So we can only get a sample outcome from this reward, but we do not know the internal, like the distribution of the reward, right? So with this as input, we want to determine a sequence of actions, and each of these actions will be in the range between 1 and k. Right. So what we do is as follows. We initialize this r to be equal to 0. So that's current reward. It's just a temporary variable. And then for every action 1 to k, we create a Q value, and that Q value initialized to 0 for now. And then we also have this counter variable, which is n, and initially it's 0 because we haven't really performed any action yet. So what we do is we do this. We go into a loop repeating t steps. With each iteration, we select some action uniformly randomly from the set of all the possible actions, and the probability will be epsilon, right? So epsilon is a parameter, and it represents a probability between 0 and 1, and with that probability we essentially perform a completely random choice. Right. But so with the other, then there's 1 minus epsilon probability, we actually adopt a greedy choice, and the greedy choice with respect to the current Q value. Right. So remember, Q value reflects what we think about the reward from the actions. So this step will be that we adopting the action that we think for now is the best, and this action adopts the action that's just completely random. So this corresponds to exploration, and this corresponds to exploitation, and then we are using this parameter epsilon to balance these two acts. With epsilon probability, we explore. With 1 minus epsilon probability, we exploit. Right? And once we do that, we can take the sample from the function r, so that would give us the reward for now. And then, sorry, I think that's a mistake. I think this v is r. Right? And then what we do is we update the Q value according to the rule that I just defined in the earlier slide, right? So once we update the Q value, then we also add 1 to the current counter for this action, because later on we're going to have it as part of the step size. So we repeat this to generate the sequence of actions, right? So this is what we call epsilon greedy selection. Right. The next question is, how do you determine epsilon? Like what I said, epsilon is a probability value, and essentially it's the probability that we perform exploration within an iteration. And if we use epsilon greedy, it means that we're fixing this epsilon. It could be high, could be low. If the outcome is relatively certain, so if we're quite sure about our expected reward Q value, then we don't need to explore that much. So this means that if we already have a rough idea about the taste of the ice creams, then we don't need to try a lot of different types. We just can, go for the one that we think is the best, right? So a smaller epsilon would be suitable, things like, 0.1 or maybe even smaller, 0.01. But if we know nothing about the reward, so if the outcome is still quite random, maybe we haven't really tasted a lot of ice creams before, then a large epsilon will be more suitable, right? Because this will give us more knowledge. If you see that, then this suggests a slight modification of the epsilon greedy strategy, where the epsilon can really change as t becomes larger. So, for example, we can set epsilon to be equal to 1 over the square root of t. So as t gets larger, then the probability of exploration gets smaller and smaller. So hopefully this strategy will also give us a better performance. But for now, let's just keep it simple. Let's just say that we fix this epsilon, and then we want to evaluate the learning process. Right. So using this example, so now we see that this example consists of 10 potential actions, and each action have a reward that's ranging between -3, well, some of them could be even -4 to +4. Right. So these actions are somehow normal distributed within this range with different min and with different variance, right? So all of these are randomly generated, and then of course this distribution is not given to the agent, and then we use epsilon greedy to try to decide on a number of samples, and hopefully with more samples that we take, we want to optimize the total reward that we get, right? What if we set different epsilon value? For example, if we set epsilon to be 0.1, if we set epsilon to be 0, when epsilon is 0, this means that we do not perform exploration. We only perform exploitation. And you can see that with this, essentially the reward will increase to a level, and then it essentially got horizontal. Right, so there's still some sort of randomness going up and down, but overall the trend is horizontal. It never moves up. Right, this is showing the inherent problem with those exploiters. Right, once you are sort of fixed about your decisions, then you are really not able to improve your overall reward. However, if you are adopting a epsilon value that are bigger than 0, say 0.1 or 0.01, you can see generally an increasing trend continuously upwards as you take more and more samples. Right, so the horizontal line is the number of samples we take. And also there's a difference between the case when we have a large epsilon and a smaller epsilon. So with a large epsilon, generally we are able to improve faster at the beginning, as shown in this curve. So the reward improves a bit faster because we are able to perform more explorations to get more knowledge and with a fewer number of steps. But it also gradually sort of stabilizes after a while. While we because we are always adopting this epsilon, which is quite big as exploration. So even though we have gathered quite an accurate estimate for the actions. If we still use 0.1 exploration, this means that we spend quite a chunk of time making these suboptimal actions. So this will really slow down the improvement on the overall rewards as the number of steps increases. However, if we have a much smaller epsilon, then you can see initially the total reward does not increase as fast, but it's continuously increasing. And if we increase the number of steps, say 2,000, 5,000, and so on, you will see that eventually the red line essentially catches up with the black line, and even gets higher than that. Right. So that's sort of comparing the different trials for epsilon greedy method, and epsilon greedy method it would be used as a main, like a building block in designing reinforcement learning algorithm. Right. And now we move on, because we have so far been just looking at a very simple case where the environment does not change, and then we make a number of samples out of the environment, and what we wanted was just evaluate those actions, right? Because there we can essentially ignore the state of the environment. But what we have now is as a general MDP, we have more than one state, and the state have transitions among each other. It's just that we do not know of these transitions so far. So we will still want to solve the optimal control problem, because that's eventually what we want to do, right? So suppose we have no model. The model-free optimal control problem asks for a policy that maximizes the long-term reward of runs, but we assume that the transition and reward functions are unknown of the underlying MDP. So we can essentially adopt very similar idea as the solution to the K-armed bandit problem. We can, for example, take sample runs of the MDP. We can take a finite number of samples, and out of the sample we can calculate the action, the reward as a result of the actions that we take. And this reward will be used by us as experience, and that indicate to us how good the sequence of actions are in terms of how much reward that we get. Let's consider an example where we're playing these famous casino sort of game, Blackjack, right? We have two players, the dealer and the player, and we are the player, right? We're facing an unknown dealer. And initially, two cards are dealt to both players. We assume that there's an infinite stack of cards, so there's no need to count the cards that have been played. But initially, everybody have two cards, and one of the dealer's card is face up, the other face is down, and we, of course, know our two cards. Right, and the rule says that if any person has exactly 21, the person wins. If both have 21, then of course they draw. And as a player, you have a decision to make. Either you want to hit, this means you want to take another card, or stick, this means you stop requesting and review your overall sum to the dealer, and then you can compare. If anyone goes over 21, then automatically you're out. Right, so you lose this. So the winning condition, if anyone gets bust, the other person wins unless both of them go bust, and there's a draw. If no one goes bust, then you're basically comparing the sum of your cards. Whoever gets a larger sum wins the game. Right? And also the value associated with the card is like this. Whenever you have card between 2 and 9, you have exactly the number on the card. If it's a card J, Q, or K, then each of these cards is worth 10 marks. And if you have ace, then it's either 1 or 11, depending on how many points you already get. Right? If the overall hand that you get sum up to a value that's less or equal to 10, then and if you have an ace, then this ace can be used as an 11 because it will be counted as 11 without making you go bust. Right? But if the sum of the other card already gets higher than higher than 11, right, or equal to 11, then with that ace, it's impossible for you to count it as 11 because otherwise you go bust. This means that this ace will only be counted as 1. Right. So essentially, the ace have its two states. Either is usable as a true ace. This means you can use it as 11, or it's unusable, that you have only one value associated with that. So we can actually model this as an MTP. What are the states? Right. The states consist of, from the player's point of view, the states consist of the dealer's showing card. Remember, the dealer has two cards and one of them is showing, and it could be either ace or could be any of these values from 2 to 10. And also our current sum. And if you think about it, we can have cards with current sum in any value. The lowest will be actually 4, right? So if you have only 2, then we have the lowest 4. The highest could be 21. Right? This means that we're going to have an ace together with a 10. Right? But if we have any value that are less than or equal to 11, right? That are less or equal to 11, then if we call another card, it doesn't really make us go bust, no matter how much value the new card is. Right? So in this case, the sensible action will always be to hit. Right? This means that here, if the total sum is less or equal to 11, there's no choice for us but to hit. So we only care about the situation where it's possible to go bust. Right? And at that moment, this is when we actually need to consider whether we want to hit or stick in the next iteration. So we just take only those states from 12 to 21. So that captures the sum of the cards that we have. But this is assuming that we always hit if the sum is lower or equal to 11. And then thirdly, we have another state indicating whether the ace that we are holding, whether we are holding an ace that we can use as 11. Right, so this is only a binary sort of feature. So now each of these two features have 10 possibility, right, possible outcomes, and this feature has 2 possible outcomes. So altogether, the number of states will be the combination of all 3. This will be 10 multiplied by 10 multiplied by 2. So I have 200 states in our case, and we would like to learn a policy that, given the state, we want to decide to whether hit or stick. Right? And what would be the best strategy for us? Hopefully, we want to do this. And how do we do this? We do this through experience. We do this through playing the game. So actually playing the game and receiving rewards. And out of those rewards, we will be hopefully iteratively improve our performance, eventually going to converge to the right decision, right? The optimal decision that we want to make. And we can actually use the method which is called Monte Carlo learning. So Monte Carlo method is a general framework of a type of reinforcement learning algorithms, and it's typically used for episodic tasks. So this sort of tasks are finite length tasks. These tasks are things like pathfinding or chess play, where the player would engage in a sequence of actions. Right? So these sort of tasks has a natural period where, starting from the first action, it goes through a finite number of steps until it reaches the final conclusion. So it never goes forever. And for each run of that game, this is what we call an episode. An episode is of this form, where we're starting from an initial state of the environment. We make an action, we observe a reward, then this goes to another state, we make another action, observe a reward, and so on, all the way to the tease state. Right? So we actually performed T actions. No, sorry, we actually performed T actions. And there are two Monte Carlo methods that I'm going to present. One is called the on-policy Monte Carlo method. The other is called the off-policy Monte Carlo method. The on-policy Monte Carlo method is the learning paradigm where we are learning about the strategy as we play a game, right? So as we take samples. So the samples are generated by the strategy that we are actually learning. This is called on-policy because we are actually learning the policy from performing this policy, from following the policy. And there's another paradigm which is off-policy Monte Carlo. This will be we're learning an optimal policy, but the experience was not generated from the target policy, but rather from a different policy. And that's slightly more complicated than the on-policy Monte Carlo, so I was presented after on-policy method. So we first of all look at on-policy learning. It treats the target strategy as this strategy pi, and you can see that this is a probability distribution that's defined on the pair of states in action, because this is essentially the same as the K-armed bandit, but here the difference is that we have more than one state. So when we're deciding what to do, we should also be on the state, relying on the state as well as the action that the player perform. So this pi would be a probability distribution that tells the agent what to do given the state. Right? And that would be a sort of a behavioral strategy, if you recall the game theoretical lectures that I presented earlier. So we say a state action pair SA is visited in an episode of the state S is visited and action A is taken in it in one sampled episode. Right? So now we let Q pi of SA. So you can see that this is really generalizing from the K-armed bandit problem, where not only the parameter consists of A but also S, the state. So that Q value is defined over states and action pairs. So that would be the expected return to the player after a play following the strategy pi had visited SA. Right, so if the play has visited, so at state S, the play actually in the player adopts action A, then we are counting that outcome into this Q value. Right, so basically expected return after play following pi visit SA, taking action A, and thereafter following the policy pi. Right. So more formally, this Q pi SA would be the expected value for all of these returns. Right. So this will be quite similar to the expected payoff in when we're looking at optimal control problem for MDPs. Right. And we're going to discuss two related problems, strategy evaluation and optimal control. That also these problems we have looked at in the MDP case where it's model-based. But here we're looking at these problems but without knowing the model. So we're looking at the model-free version of these two problems. So the on-policy Monte Carlo strategy evaluation algorithm takes as input a policy pi, and the output will be the estimated Q function for all the states and action. The initialization phase sets the Q value to 0 for every pair of SA. And also we created an empty list for every SA. We call it return SA. So this records the reward that we get out of the pair SA. And then to compute the empirical min, so first of all, the algorithm generates an episode using the strategy pi by running the unknown MTP. So even it's unknown, we can still run it as a black box, just like in the k-armed bandit case. And if we follow the strategy pi, even though this pi could be probabilistic, we can still just take actions that are consistent with the probability specified by pi, and this will generate a play. So this will be an episode. Remember, we're looking at episodic tasks, so there's a start and end to this episode. And we're starting from S0 until we reach the last state ST. Right, so we go through exactly T steps. And then for each of the step, what we do is we want to compute a valuation. And this valuation, so this G will be this valuation for the action at this particular episode. So if you, for example, if you consider one of the actions, right, one of the state action pairs that have been visited by this episode, what should be the expected reward that we attribute to this action? Right. So here we're assuming that all of these rewards that we get at the steps that follows, the episode has visited the pair S1A1 to be the consequence of us performing this action A1 at S1, right? And therefore, so all of these can be attributed to this decision, and therefore we can obtain a sort of a averaged reward for all of these episodes, starting from the step where the action has taken place to the very end. We look at the average reward in this form, and that will be G. Right, we do this for every t from 0 up to t minus 1. So for every step in the episode, we are calculating an estimated reward that can be attributed to that step's decision. And we assign it to G. And then we just append G at the end of the list returns. And then we just calculate the average among all of the values in the returns for a specific pair of ST and AT plus 1, and this will be assigned to the Q value of ST and AT plus 1. Right? And this finishes just update of Q value for this pair of ST and AT plus 1, but we do this for every pair of ST and AT plus 1 that we have seen, right, until we processed the entire episode. But then we repeat it. We repeat it for an indefinite number of times for as long as we can take, more samples, and then we terminate. And after that, we output the Q function, which is our estimate for the Q value, the evaluation for this SA pair. So to illustrate the algorithm for strategy evaluation, let's recall the Blackjack example. We need to fix a strategy for the two players that are involved in this situation. So, of course, because we're trying to assume that the underlying situation, in fact, is a Markov decision process, so let's assume that both players will be playing a Markov strategy. So this means that given the current state, the player would just adopt a corresponding action. So let's look at the dealer strategy. Assume that it is that the player will choose to stick if the sum of his card is 17 or greater. But if it's not, then hit. All right. And then let's look at the player strategy. Assume that it is that to choose to stick on any sum of 20 or 21, and otherwise hit. All right. So these are the strategy of the players. And then we haven't really specified the immediate rewards of the players. So I'm just saying that if it turned out that the player, so the winner would get actually +1 and loser would get -1. And of course, if it's a draw, then both players will get 0. And let's assume that this is undiscounted. So it's just lambda is equal to, the discount factor. In fact, I think we assumed that it was gamma, which is equal to 1, right? So now we want to evaluate the player strategy given the dealer strategy, which is fixed as above. So we fixed dealer strategy, and now we want to evaluate player's strategy. And then we use the algorithm, namely the on-policy Monte Carlo algorithm to evaluate the strategies. And here we are using the diagram to represent the expected payoff of the players at different states. So we can see that according to the strategy, there are actually 4. We break it up into 4 different conditions. The first column indicates the result of the evaluation after about trying 10,000 episodes of the game, and then the next column indicates the result after trying 500,000 episodes. Much more number of samples that we took for that one, and you can actually see that when we take many more samples, the evaluation, it gets very, much more smoother than the previous case. And we can clearly see a pattern here. The sort of the horizontal and this axis, they combine to represent the states of the game. Namely, we have one axis denoting the card that the dealer is showing, and another axis denoting the current sum of the player. Right, so they correspond to one of the states, but of course we have also 2 cases where either the player has a usable ace and no usable ace. So we separately illustrate these 2 situations. If it's a usable case, if there's a usable ace, then we look at the first row, right? The top diagram. It clearly shows that if the player sum is actually gets larger and tends to 21, then the expected payoff to player will get larger, so it moves towards +1. And when the player sum is actually quite low, then it gets more towards -1. Okay, now we move on to discuss the problem that we were aiming to solve, namely the model-free optimal control problem. Remember that assumes an underlying Markov decision process, and which is unknown largely to the agent. And the agent would need to perform a number of trials and then use Monte Carlo learning in order to find the optimal policy in order to achieve best performance in the Markov decision process. So we could, of course, adopt a very similar strategy as in the model-based case. Remember when we were using dynamic programming and then design the algorithms like policy iteration and value iterations to solve the optimal control problem. And in fact, this is exactly what we're going to do. We will alternate between 2 phases, the strategy evaluation phase and the strategy improvement phase. So this comes with almost the same as the dynamic programming case when we would not know about the optimal strategy. So we just start with some arbitrary strategy. And then iteratively we evaluate the strategy and we hope to improve it. But now the difference between the previous case and here is that we will not be able to get the exact evaluation, the true evaluation. We will get some sort of estimated valuation, which were derived from our experience, but eventually it does the job. Right. We're gonna modify the previous policy iteration a little bit. So instead of doing the entire evaluation and then move on to improvement and then repeat an entire strategy evaluation, what we do is we just perform one-step strategy evaluation. So this means that we are basically following a similar strategy as in the value iteration algorithm. We only look at just one step from any state to the other state. So basically perform this one step of the strategy evaluation and then directly will apply a greedy strategy improvement. So the picture still very much look like the policy iteration algorithm. But one thing, in order for the Monte Carlo algorithm, the Monte Carlo learning to succeed, we will need to make an assumption, namely exploring start assumption. So this is actually quite strong. Assume that every state action pair would have a non-zero probability to start an episode. So essentially, if we take more and more samples, we'll be able to cover all the state action pairs that are possible in this underlying MDP infinitely many times. So for every state action pairs, we'll be able to accumulate enough experiences so eventually we will be able to get a better prediction on the value of that state action pair. Right, and we could, under this assumption, we could actually prove that if we use this sort of iteration between strategy evaluation and strategy improvement, this method actually converges to the optimal policy. So this actually solves the question that we want to solve. So now the question is whether the requirement that we have exploring start is reasonable. So remember that exploring start is actually a very strong assumption. It says that under all the possible states, we would, if we take enough number of samples, we will be able to generate an arbitrary number of samples that visits that state and action pair. Right? And when there are lots of states in the space, if we just simply play MDP according to the strategy that we are currently trying to optimize, it is very unlikely that we will be able to explore all the possible state action pairs infinitely many times. So eventually, most of the state action pairs will be eliminated from consideration. And this is the opposite of what we wanted to do. Right? So again, we're running into the dilemma here between exploration and exploitation, right? So in order to accommodate this problem, we will again need to have this exploration phase, and epsilon greedy is a strategy that's convenient for us to solve this issue, right? So what we can do is we can say that, well, with certain we can reserve a portion of time where the agent will perform exploration, and this exploration may lead us to an arbitrary state action or arbitrary action. But in most of the other times, we get just follow the greedy strategy improvement. Right? So the difference here is that we would be able to allow the agent sometimes to deviate from the strategy that currently is seen as the optimal choice. So what we can do is this, we can define a strategy that is epsilon greedy. So we'll first of all fix epsilon, which is a probability between 0 and 1, and hopefully that's not a very big probability. Then we can get pi of SA. Remember, that's the behavioral strategy, so that captures the probability of choosing action A at state S, and then we assign the probably 1 minus epsilon plus epsilon divided by the number of actions of the player, right? And then if A is the greedy choice, and if A is not the greedy choice, then the probability would just be epsilon divided by the number of actions. So this is essentially saying that, well, with probability epsilon, we just randomly choose any action, and this also includes the greedy choice action, right? And then with probability 1 minus epsilon, we definitely choose the greedy choice action, right? So we can put in to the algorithm this epsilon greedy exploration, and then we also combine with the policy, the strategy evaluation, strategy improvement idea to get what we call the Monte Carlo control. And notice that here the experience that we use for training the strategy actually was derived from the strategy itself. And this is why we call it an on-policy algorithm. So it's an on-policy MC control algorithm. Like what I said, we start with some initial value of the Q. It could be 0, for example, for every pair SA. And then also we initialize this strategy pi and just assume that it's just random walk, right? So starting from any S and A, any action will get the same probability of taking place. And then we go into this learning phase. So we iterate. So we iterate a number of rounds. At each round, what we do is we generate an episode using the strategy that we currently have, which is pi, and that episode namely will be S0, A1, R1, S1, A2, R2, and so on, all the way to ST. And then for each step in that episode, and notice that we're going backwards now just to make the computation convenient. We are actually calculating a sort of summed payoff that are attributed to the state ST with the action AT plus 1. Right, so we calculate this value, we store it as G, and then we append G at the back of the list of return STAT plus 1. So this is all the same as the strategy evaluation, right? So we do this for every step in that episode, but we only do that once. And then, of course, then we update Q, right? For every ST and AT plus 1, we update the value of Q as a new average among all of the returns that we get in the experience. So we're actually using the empirical average as a estimate of the actual expected payoff for the player. And then that finishes one step of strategy evaluation. So after the strategy evaluation, we'll get a sort of a improved version of the estimate, because from the sample we derived certain experience, and this experience is used to update our estimate of the Q values. And then we go into this blue phase, that's the strategy improvement phase. And there we simply adopt a update. And there are two forms of update. There is the greedy update for the strategy, and there's a possibility of exploration. So exactly what we do is we look at the action which gives us the maximum Q value, right? This is based on the current Q value that we have estimated, right? Which is, the result of all the samples that we have taken so far. And then A star will be that action which give us, so from any state, A star will be that action which give us the maximum Q value. And then we apply this epsilon greedy mechanism to possibly set the current strategy to a random action, but most of the times with probability 1 minus epsilon plus epsilon divided by A, the updated action will be the action A star. Right, so with that, you can see that this is not 100% strategy improvement, because there are quite a lot of uncertainty here. One of the sources of uncertainty is the function Q is in fact not a precise function which describes expected payoff of the player at state S and following action A, right? Because that's only an estimation, and because of the estimation, it may not be the true payoff. Right, so that's one of the sources of uncertainty here. And then the other source of uncertainty will be the adoption of the epsilon greedy strategy, because with certain probability, the updated strategy could be an arbitrary action. Right? Nevertheless, it occurs quite rarely, and through time, the Q function will get more and more precise. Right, and so hopefully whenever we perform a greedy update to the strategy, we will be able to actually improve the current strategy. Right, but you can see this is how we settle the exploration-exploitation dilemma, but this is not very ideal. Because of the way we implement epsilon greedy mechanism to allow exploration, we in fact have destroyed the guarantee to optimal strategies, right? Because epsilon greedy just says that at some point you are able to, the agent could move in some arbitrary way. Right, no matter how small that probability is, there is some non-zero probability that the agent would, not function in an optimal way, and therefore we cannot guarantee that the strategy eventually after convergence will be the optimal strategy anymore, right? Because of epsilon greedy, but we can guarantee something else. Right, so we can define a strategy pi to be epsilon soft, because we're looking at soft strategy. So pi is called epsilon soft if the probability of choosing an action at a state S is greater or equal to epsilon divided by the number of actions for all the states and all the actions A. Right, so this is sort of like a requirement for a strategy that says that you definitely can perform exploration for every state and for every action up to certain probability, and this probability is we know that it's bounded by epsilon divided by A. Right, so notice that this epsilon greedy exploration strategy itself is epsilon soft. And once we have this condition put in place, then theoretically we can show that with the on-policy MC control algorithm, it will eventually converge, and it will converge to a strategy that is the optimal epsilon soft strategy. Right, so the bad news is it does not guarantee optimal strategy, but the good news is that it guarantee the optimality among those epsilon soft strategies, which is still a good case if you would allow the agents to from time to time explore a little bit. Right? So that's the on-policy control. So Monte Carlo control. We could, for example, look at this Blackjack again, and apply the algorithm that I described, and then we can get this optimal policy for the player. And you'll be able to see that, of course, the action depends on the current state, and the state depend on the dealers showing the current sum of our cards and whether we got a usable ace or not. So we have these two cases, and you can see that I'm using two plots to illustrate the optimal action that we should take. That's the action that's specified by the strategy after the algorithm converges. And you can see that here very much when we have a usable ace, the best strategy will be to, whenever our sum of cards is at 18 or above, for most of the cases, we will choose to stick, and otherwise we choose to hit. Right? But this is very different if we have a usable ace. If we have a usable ace, we would see that even when we do not have a usable ace, we will see that when the player's sum is only about 12 or above, when the dealer is showing a card of 2 to 6, we should, in this strategy, to choose stick, and otherwise we choose hit. Right, so the bar for calling to a stop of this episode is much lower than in the case when we have a usable ace. Right, so that's just the outcome of the strategy. But bear in mind that this is strategy which is not necessarily the optimal strategy. It's only the optimal strategy among the epsilon soft strategies. Right. So next we want to look at off-policy Monte Carlo optimal control. Remember I said that there were two types of Monte Carlo algorithms, and we'll look at the on-policy learning. It has the advantage that it's relatively simple to design and implement because it essentially just follows the same idea of policy iteration in the model-based case. So it's like we're just replacing the Q value, the Q function, from the actual reward function to the sort of sampled or empirical average reward function. So otherwise it's almost the same. And also it enjoys fast convergence speed because we are updating the policy as we're learning. But there are some severe disadvantage of on-policy learning. First of all, like what I said, on-policy learning can be guaranteed to not find the optimal strategy, right? Which is sort of like we know for sure that this algorithm will not solve the problem because of exploration. And when we have exploration, there's no way that we can always choose the best action. Another quite subtle problem with on-policy learning occurs in reality. In practice, we would want to apply this learning, but we don't have the luxury of directly running the strategy that we have computed. Right? So sometimes learning multi-step predictive models of the world's dynamics, for example, we will only be able to get some previous observations of episodes, but we cannot actively collect new episodes from the policy that we have at hand. And also the sample cannot be generated. So sometimes the samples cannot be generated for the target strategy, but rather we can obtain some other behavioral strategy. So there's a departure between the strategy which we are trying to optimize and the experiences which we rely on for training. Right? So, with those constraints in mind, it would be important to design a so-called off-policy learning. And this is a learning which relies on experiences that are off the target policy. Right? The good thing about this paradigm is that no longer we're working with soft policy, because our goal is to find the optimal actions, and this should be pure strategies. It says, okay, with this state, you should definitely play this action. Right? So instead of a probability distribution, which involve a degree of exploration, or random exploration there, we would definitely want to say that, okay, from this state, the best action is to do this. Right? So here, off-policy learning allows us to obtain a pure optimal strategy. Right? And another very good side of off-policy learning is that the experiences that we use can be some sort of observation, or can be some old strategies, and so on. So it doesn't have to always be the target strategy that we are trying to optimize. Right? And also, just from a theoretical perspective, we could guarantee optimality with off-policy learning, whereas in the on-policy learning, this is not possible. Right? Because in the policy that we try to use as target, we would not implement exploration at all. So that's the advantage of off-policy learning. And we could repeat the solutions above for the problems above. First of all, we're facing strategy evaluation problem. Right, this is the problem. If given a strategy, we would like to obtain the Q function. So, from the sampled episodes generated by, a behavioral strategy B. Right. So now we have these two strategies. We have the pi, which is a target strategy. We have a observable behavioral strategy. And we assume that, from this behavior strategy, it is possible to obtain more and more samples. Right? For the next algorithm to work, we still need to make an assumption. This is based on the relationship between the target strategy and the behavioral strategy. It says that whenever there's an action that could be played by the target strategy, this action must be able to be played by the behavioral strategy. Right? So basically it says that the behavioral strategy to be somehow covering the target strategy. So that's all we need for the behavioral strategy. Right? And in the off-policy strategy evaluation, one of the very common technique that we borrow from statistics is importance sampling. So it's a general technique for estimating the expected value under one distribution, but given samples that were taken from another distribution. And suppose we have these two distributions, P and Q, and we would like to obtain expected value of P, but how do we do it if we only have samples from Q? Well, what we could do is we look at the formula that are shown here. We want to evaluate expectation of fx, where x is taken from the probability distribution P. And this will be the same as the sum of all of the possible outcomes of the occurrence of the probability of occurrence of the outcome multiplied with the value of f of that outcome. So px times fx, and of course px is equal to qx times px divided by qx. Right? And after summation, we essentially get that in order to evaluate the expectation with respect to the distribution P, what we could do is we can take samples with respect to distribution Q, but with every value fx, we should multiply with px over qx. Right, so as long as we have px and qs both, then we'll be able to quite easily obtain the expectation with respect to the probability distribution P instead of Q. And how do we apply importance sampling to our case? Given a start state St, the probability of the subsequent episode, namely AT plus 1, ST plus 1, AT plus 2, and so on, all the way to ST, occurring under a policy pi will be written formally as the probability of that episode, given that all of these AT up to A capital T are sampled from the probability from the strategy pi. And we can actually expand this probability out so that this will be equal to pi of st of at plus 1 multiplied with the probability of the transition from st to given st at plus 1 to st plus 1, and then multiply with the probability specified by pi for st plus 1 and at plus 2, and so on and so forth. Right? So we got this expanded form of this probability, and then we can look at importance sampling. So we define importance sampling ratio as the relative probability of the trajectory E under the target and the behavior policy. So we have these two policies, pi and b, right? So we define basically rho with the superscript E, so the subscript T column capital T minus 1. So you see that the superscript indicates a trajectory, and the trajectory is a sequence of actions and states, right? So this is defined as a ratio between the two probabilities. One is the occurrence of this trajectory, which is consistent with the target policy pi, and the denominator will be the probability for this trajectory, which is consistent with the behavior policy b. And then we can see that in the expanded form we have the probability which is unknown to us, which is the transition probability, but we can actually cancel because both top and bottom are just products, so we can actually cancel all of the factors that involve the transition probability of the Markov decision process, and then in the end we just get the product of all of the ratios for the state action pairs sk and ak plus 1 between pi and b. Right? So that will be the importance sampling ratio, and in order to obtain an expectation for the Q value with respect to the target policy pi, but suppose we only have the Q value with respect to the behavior policy B, what we need to do is just to multiply that with the importance sampling ratio. Right, so this is what importance sampling gives us. So now we formally describe it in this way. Suppose we take a sequence of sampled episodes E1, E2 up to EL, and then we define this calligraphic T with a subscript K with the parameters S and A to be the set of all the stages from 1 to T minus 1 in which the pair SA is visited in the K's episode. Right, so that's the basically a set of stages given an episode EK. Right. And then we define this G of K GKT, so G subscript KT, to be the sampled return in that episode EK, but starting from stage T to capital T. Right? And then we collect all of these GKTs where T is taken from calligraphic TKSA. So this will be the set of all of the possible sampled returns from these episode EK, which visited SA, and for all of the possible Ks between 1 and L. Right? So essentially this captures suppose we have E1 up to EL, which are our experiences that are obtained from the behavioral strategy B, right? So this set capture all of the sample returns out of this experience, of the entire set of experience that we obtained from the pair SA. Right, so essentially, we can use that as a data set for us to estimate the expected payoff for the pair SA. Right, so now we can define two important sampling methods: ordinary importance sampling, which is just to calculate the average value among all of the GKTs which fall into the set that I was talking about. So we take the sum of that and divide it by the number of elements in the set calligraphic T with the subscript KSA. But of course we need to multiply with the importance sampling ratio because we are performing importance sampling here. And then we add everything up for all of the K between 1 and L, and for all of the T that are belonging to TKSA, right? And this, as more and more iterations are carrying out, we'll say that eventually the result of that will be our estimation QSA. Another possible way of implementing importance sampling is what we call a weighted importance sampling. So in this case, we do not just take the average among basically the visits of all the occurrences of SA in our experiences, but rather we take the sum of the product between row EK T2 capital T minus 1 times GKT, but then we take the sum of everything and then we divide it by the sum of all of the importance sampling ratios, right, for this SA, right, and that gives us Q of SA, right. Note that weighted importance sampling normally give out a smaller variance from ordinary importance sampling. There are some subtle differences between these two methods, but the best way is to look at an example, which I would not elaborate here. But let's, for now, adopt this weighted importance sampling method in carrying out off-policy Monte Carlo learning. So if we go back to the example of Blackjack, we want to compare ordinary importance sampling with weighted importance sampling under certain suitable setup of the other parameters, and then suppose we run number of episodes, and this is the result that we get. Vertical axis indicates the mean square error between the estimated Q function and the actual Q function. And you may see that, okay, both of these importance sampling method actually tends towards mean square error 0, so they eventually become correct. But you can see that at the initial phase, when there are not many episodes, ordinary importance sampling actually give out a big variance, whereas weighted importance sampling only have a very small error. So that's it shows that weighted importance sampling has some advantage in practice. Now let's continue to discuss off-policy strategy evaluation. We want to approximate this Q function using the behavior strategy B, and that combined with importance sampling, of course. So what we want to do is we compute a sequence of values, namely these QNs, where on top, so each of the QN will be a fraction. At the numerator, we'll have certain weight, WK, multiply certain value, GK. That it's equivalent, and then at the denominator, we have the sum of the weights of K. So that's equivalent to the weighted importance sampling. It's just written every term with a sort of simpler symbolic form. Right, but if you think about it, it's exactly the same structure as the weighted importance sampling. So this is the value that we would like to compute, and when it converges, when this QN converges, that will be the output of the algorithm. So we want to adopt a incremental method. So instead of every time evaluating these value Qn, what we do is we want to update Qn plus 1 from Qn, and then we iterate in this way until it stabilizes. So we change this formulation to an iteration, to an incremental implementation, and you can actually see that it's not so hard to derive from the above to a pair of simultaneous equations where we have Qn plus 1 is equal to Qn, which is the evaluation in the last stage, plus the weight n divided by certain Cn, multiply with Gn minus Qn. Okay, and what was Gn? Gn was the actual payoff that we obtained from those samples, and Qn was the expectation that we take. So Gn minus Qn will be the error that we're trying to minimize. And so basically you see that this again will be in line with the, if you recall, the KM, the Bandit problem, when we have the update rule, which says that the new estimation will be equal to the old estimation plus some step value multiplied with the error. Right, so that's exactly the same form. So now the next question is, what is the Cn? So in fact, Cn plus 1 can be also updated from Cn by just adding an extra weight, Wn plus 1. And of course, initially we have C0 equal to 0. So instead of computing these Qn according to the formula above, what we do is we apply the formula below for Qn plus 1 and Cn plus 1 in an iterative algorithm to repeatedly update this Q function. So now we are able to write down the off-policy version of the Monte Carlo strategy evaluation algorithm, assuming we're using weighted importance sampling. The input will be a given target strategy pi, but we would like to evaluate this strategy using a behavioral strategy B, and then assume that's the only strategy from which we can take samples. And what we do is we, of course, initialize this Q function as 0 in the beginning, and then we go into this loop, and within this loop, at every iteration, we use B to generate an episode. And then what we do is we essentially repeat very similar as the on-policy method, but now the difference is that we were using the pair of functions for C and Q in order to essentially use important sampling to help us to update the value queue. Right, so this is just an implementation of the procedure that I have just described. So now we finally come to describe the off-policy Monte Carlo control algorithm. You can see that the algorithm follows a very similar structure as the strategy evaluation algorithm. In fact, a large part of it is performing exactly those operations in the strategy evaluation algorithm. The clear difference is that now we are no longer given the target strategy pi to evaluate, but instead we're starting we're starting the algorithm by initializing a strategy pi, which isn't just an arbitrary strategy. And then our aim is to, through evaluating this algorithm, we are able to perform greedy updates to the through evaluating this strategy, we are able to perform greedy updates to the strategy and improve its performance, and then we repeat the evaluation. So essentially, we're adopting a very similar pattern as the policy iteration algorithm. Notice that I've colored the lines using green to represent those operations that are working towards evaluating the current target strategy, and then the blue operation is the one where we perform the greedy update. So you see that there is this right. So we can be sure that so one can actually prove. So repeat. So one can actually prove that under the coverage assumption. Remember that assumption assumes that whenever the target strategy has a non-zero probability of adopting a action in a particular state, the corresponding behavioral strategy also has a non-zero probability of doing the same, right? So in this sense, we're saying that the behavioral strategy would be able to cover all the probabilities of the target strategy. So under this assumption, the off-policy Monte Carlo control will converge to the optimal strategy pi star. So this is an off-policy control algorithm, and therefore we can guarantee that this pi star is indeed the optimal strategy that we were looking for, right? So now we finally come to an end to today's lecture. We've started to explore the case where the underlying MDP, namely the model that captures the dynamics of the interaction between the agent and the environment, we start to look at the case when this model is unknown. Right? And when this is the case, there's a need for the agent to gain such knowledge through taking sample runs of the MDP and observing the corresponding rewards. And in this way, we're able to compute an evaluation function, namely this Q function, that for any state and action, we aim to estimate the return to the player if the player adopts this action A from A state S. So the algorithm, the learning paradigm that we adopt was reinforcement learning. And in this paradigm, one of the key issues is exploration-exploitation dilemma, which calls for a balance between trying to improve the current behavior in the currently seen as the optimal way and the the action of just exploring the different options and potentially suboptimal operations. Right? So we actually used a very standard method, namely epsilon greedy method, to solve this dilemma. And we've illustrated how this is used to solve the multi-arm bandit problem. Essentially, that's the optimal control, or you can argue it as some sort of control, but without the environment being changing, right? So there's only a single state in the MDP, and what we're getting is just we're trying to learn the reward function out of all of the actions there. But we could actually extend all the ideas to MDPs in general, and more generally, we've looked at Monte Carlo method that's able to generate sampled episodes from the MDP. And in order to solve the optimal control problem for this case, we've described two sort of algorithmic paradigms that's within the Monte Carlo methods. One is on policy, the other is off policy. The on policy is more straightforward. Essentially, it's adopting a policy iteration framework, but it improves on the policy based on an estimation of the actual return of the player, right? And the off-policy learning is different from the on-policy learning because the experience of those sample episodes that were generated not from the target strategy that we aim to optimize, but rather from a different behavioral strategy, right? And then we apply importance sampling to use those episodes to learn about the target strategy, right? And then the rest was very similar to the on-policy method, where we again iterate between the evaluation of the current policy and the improvement of the policy in order to converge to the optimal strategy, right? So that's what we have covered in this lecture, and I'll see you in the next lecture.